measurement equipment. Also some other devices and systems that, well, that are not so related with test and measurement, but always very linked to communications, electronics, RF, microwave. Okay. So today we will be talking about what is going on right now in high digital interface testing and validation. What are the new techniques that are really giving new advantages and new benefits in digital testing? So some of the concepts we are explaining today are not new, but what we will show are some add-ons that are really coming into the industry and are really leading the way to the digital testing, digital communication testing. So first of all, we will do a summary of what are the main techniques to make high-speed digital interface testing, and then we will talk about some things that most of you are aware of, like eye diagram, for instance. But what is new on this way of measuring digital buses? Okay, real-time eye diagram. We will talk a lot about this and what it really means. And also TDR, TDT for validation of PCBs and circuit design. So I guess most of you may be aware about these kind of things, of course, but we will talk about new improvements that are really coming with force into the industry. So when we talk about testing high-speed digital buses and high-speed digital interfaces, we could split into two main groups: the use cases and the techniques. One of them is the compliance tests. In this case, we want to be compliant to some test specifications, some standardized buses or standardized interfaces like DDR, PCI, USB, and many others. So usually what we have to do in these cases is just to fulfill some test cases that are well defined. Usually what we have to do, usually the procedure is to work with an oscilloscope in a single acquisition. So we use the oscilloscope mainly as a digitizer, and then this acquisition, a long acquisition maybe, goes into a software and gives results. Okay. Usually this software could be proprietary software from the main manufacturers of test and measurements. Also, there are some open tools like SIGTest. Maybe some of you are aware about this, which allows to test PCI or USB. But this is just, usually compliance tests are just used to validate, okay, and to prove that we are compliant if we are going to integrate this design into another third-party manufacturer, or if we are going to sell this design into the market and put the logo on top of it, specifying that we are compliant to these standards. Okay, but this does not help in the development procedure, in the development process. This is just the end. But when we have problems, when we are really designing in a previous phase, what it really matters is debugging and signal integrity. We want to check our signal integrity. We want to verify that everything is going well. We want to find faults and debug, to find where they come from, what could be the cause. So now it's these techniques I'm going to talk about today come into force, to reality. Today we will be talking about eye diagrams, and specifically about real-time eye diagram. Many times many oscilloscopes and many tools can bring an eye diagram, but it's not really real-time. It's just a long acquisition, and then after many calculations, it gives an eye diagram. And it's just basic information, but it's not really helpful to test the eye diagram in real time, in real conditions, with many different kinds of operations. Okay? We will talk about real-time eye. Also de-embedding. We will talk about de-embedding. The embedding is something that is not new, but we will also talk about what are the new improvements and why we need de-embedding, of course. And finally, also we will talk about what I already told you, TDR, TDT measurements, time domain reflection and time domain transmission measurement. Usually for this kind of tools, as we are debugging and we want to check the signal integrity and find faults, we need our oscilloscope to run in continuous acquisition and to be as fast as possible. If our oscilloscope is slow, it's just it will be very difficult to find problems and to really get an idea of what's going on in our design. Okay. So first of all, well, eye diagram, as you may know, when we deal with digital signals, digital interfaces, are very common and very useful, because we can assess rise times, fall times, signal to noise ratio, jitter performance, overshooting, ringing, many parameters that can be useful to get an idea on how our signal integrity is maintained. We can, when we have a histogram with many acquisitions on top, zeros, ones on top, we can run histograms to get measurements there. For that we need a lot of acquisitions which are really overlapped. We can usually it's helpful to establish persistence in the eye diagram to keep not only what it's happening now, but what happens in some time ago. And also color grading to see what are the most probable transitions, and see where the signal is going more probable in our design. I mean, in regarding time and voltage. If our measurement tool is fast enough, we can define mask inside the eye diagram to detect violations. But for that we need the eye diagram to be really fast. Otherwise, the mask very unlikely will detect problems and glitches, transitions that should not occur, runs, okay, many different events that could happen, but if they are not statistically so probable, maybe with a low calculation, low speed measurement tool, it's difficult to detect. And usually to get a good eye diagram, we need to recover clock in case we have a clock embedding in an embedding clock in our bus. This is very common in high-speed buses. We have the embedded clock. So to recover properly the eye, we need a tool to recover, like a PLL, to recover the clock. And this way we can build the eye much more accurate and not adding so much jitter and noise. Okay. The problem so far is that if you look at the current solutions in the market, most of the solutions that are in the market, they do many calculations like clock data recovery and histogram measurements in post-processing. So what's happening there? So in the end, the oscilloscope or the acquisition tool will take a very long acquisition, and then it will post-process by software this acquisition during a long time. So during this long time, we will have a blind time. Okay. So the measurement tool or the oscilloscope will see nothing. And then we'll get a result, okay? And then the procedure starts again. The oscilloscope starts acquisition again, makes the calculation for a long time, and then shows again some results. So it's really, really slow and doesn't help to find problems and faults that could be in our transmission. Okay? So what should we need to improve this solution? So this is what we call the real-time clock data recovery. It's basically to build the CDR block in hardware. Okay, so clock is recovered in hardware, not in software. Not only CDR, clock data recovery block should be in hardware, but other important calculations that are important in high speed should be done also in hardware. Otherwise, we'll get a really, really slow eye diagram that will not really be useful for debugging. Later, we will show what it really means, real-time clock data recovery. But now let me explain you about de-embedding. So why am I talking about de-embedding? Why is it important? Why we need de-embedding? So in every transmission, we always have the signal source, the transmitter, and the receiver, okay? And in between, we have the channel. Okay, this channel could be cables, fixtures, adapters, wires, probes, many things. In case of measurement, when we are measuring a DUT, a device under test, signal source should be the DUT, and the receiver, the oscilloscope or the measurement tool. So if we do not de-embed, what we measure is the signal here in the receiver point. Okay? This is the measurement plane. What does de-embedding do? It moves the measurement plane just to the transmitter point. Okay? So when we add a channel, when we add cables, we are embedding or, well, adding channel. You come from the university world, so you are familiar maybe with these terms, convolve, filtering. Okay, we are adding a channel, we are modifying the signal. So we need to de-embed or deconvolve the effects of our path or of our channel. Okay. Why is it so important? Okay, when it comes to low-speed digital interfaces, it's not so important. It's not a big deal. The effect of fixtures, cables, adapters can be neglected. But what happens if we go up in frequency? So the effects of cables, for instance, just a 1 meter cable, for instance, of course, depending on the material, also the electric and design of the cable, but the attenuation is really dropping down, increasing, and this effect is really impacting our measurement. Actually, the signal is not only at, when we talk about digital signal, the signal is not only placed at a single frequency. It's broadband signal. Okay, we are talking about broadband signals, so different frequencies have different attenuations. So these are really impacting our eye diagram or our measurement. Not only in magnitude, but only in phase. So that's why in high-speed digital interfaces, de-embedding it really matters. Okay. So probes, cables, fixtures, everything in the middle are really impacting our measurement. And the compensation of these effects are really necessary. Well, measurement error sources or components that could affect our measurements could be impedance mismatches, probing effects, of course, cables, packaging, fixturing. There are different methods to correct these errors. For instance, using calibration. And this is the case when we use VNAs, vector network analyzers. Some mathematical signal processing, like doing equalization or something similar. And what we are talking today, de-embedding techniques. So how does it work? How is it working, de-embedding? So what we need is, so we have our measurement in our scope with our degraded signal. So we need to go back before the measurement and make some calculations on our elements that are in the chain of the transmission, fixture, cable. What we are using really are the S parameters. S parameters are very commonly used in high frequency, in microwave, as long as the system is linear, time invariant, stable systems. So we calculate the S parameters, we load into the oscilloscope, and then we de-embed. Okay, as I tell you, S parameters are very common in high frequency device characterization. And once we have the S parameters, we can, and as long as the signal is working in the linear range of the devices involved, this parameter matrix can be used. So how do I get these parameters? Maybe for some of you it's not so common to work with these parameters. The traditional method is to use a VNA, a vector network analyzer. So maybe many of you didn't ever see a VNA, because this is a tool very commonly used in the RF people, but maybe for the digital circuit microelectronics people, it's not a very common instrument. Okay, but there is also a possibility is to get these parameters using TDR measurements, which we will be talking later. But measurement reflections in time domain, we can get these parameter values of cables, probes. Maybe it's not so flexible as VNAs, but in many cases it can do the work. So for that we will need a pulse generator and time domain instrument like an oscilloscope. We will talk about this and how we can do this with our solution. Or another possibility is just to simulate our fixture or cable or whatever and extract the S parameters from the simulation. What cases could be used for the embedding? For instance, probe. When we are probing into a circuit, the probe, of course, is also changing the conditions in the circuit. The circuit is changing the signal. It has an impedance, a frequency response of the impedance. It's not constant and it's not infinite, of course. So probe the embedding is can be done, and it's important. Also, as I told you, fixtures, cabling can be de-embedded. In many cases, some fixtures are already in the market, are already provided in the market, like USB fixtures or PCI Express fixture, and S parameters are already available when we buy this board. Usually these are the most common formats. Is what we call touchstone files, which are provided by every VNA in the market. Every network analyzer can provide this kind of files. Also, for instance, maybe some of you are working with DDR memories. In this case, it's very difficult to probe, to put a probe in the DDR chip. So what many people use are interposers. Also for many suppliers of interposers, we can get S parameters. They provide these S parameters. Okay, this is an example how putting the interposer to better soldering our probe on top. Okay, so once we have our S parameters, what are we doing with these S parameters? How we use these S parameters to really de-embed? So the answer is in the FIR filters. Okay. As I told you, a linear time invariant system have a finite impulse response. This finite impulse response, if we perform the FFT, we convert into the frequency domain, we get a magnitude and phase response over frequency. And this is exactly what the S parameters are providing, the response over frequency, magnitude and phase. So the oscilloscope or the measurement tool will get these parameters, calculate the IFFT, and model this response as a FIR filter. Digital filter, digital FIR filter. So this is the procedure. We import these parameters, we get the magnitude and phase, we calculate the de-embed response because what the oscilloscope has to do is to de-embed. So it has to make like the inverse response that will provide a flat response over flat response of magnitude over frequency and linear response of phase over frequency. So in the end, what we are doing is generating another transfer function that multiplying with the existing transfer function of the S parameters will provide a flat response. So it's a kind of equalization. So once we have the de-embed response, we create the FIR filter, and then we download the filter coefficients into the oscilloscope. And here in this process is when the news are coming. The new things I'm going to tell you about today are really important. So the embedding is not, well, this could be the effect of the embedding, for instance, before and after a USB 3 channel. You can see how the eye diagram is wider now, and it's fulfilling the standard mask. So the embedding is not really new. You can find many solutions in the market that provide the embedding, but they all do it in software. So again, the signal is digitized and then loaded into the CPU, and with many calculations, it provides a de-embedding response, and we get the signal corrected. The problem here is that, first of all, it's a process that takes really long time. So the oscilloscope will be very slow. But there is also a second impact. Is that the signal we are watching in the oscilloscope is not the signal we are triggering on, because the trigger is done before in hardware. So we trigger on the signal which is not corrected, then we correct the signal. So we have something in the screen, but that is not really the signal we are triggering on. Also, if we are, for instance, if we want to recover clock, the clock is not performed in real time. It must be done by software after this software de-embedding. So it will, again, be very slow. So what are the news here that we are showing today, and we will show you also on a demo later. The de-embedding procedure is performed in hardware just before the ADC acquisition. Okay? So the signal is digitized, then the de-embedding filtering is applied, and after that, with the signal corrected, we can trigger and perform the clock data recovery on this recovered signal in real time. So the impact on the speed of the oscilloscope is not really strong. It's very few, very little, and we'll be able to perform eye diagrams and some other measurements with very fast acquisition, and also triggering on this signal, on this corrected signal. So we are really triggering on the signal we are measuring in the transmitter point, in the DUT plane. So this is very fast. As I told you, doing by software is really slow. And not only the problem with, as I told you, we don't only have the problem of speed impact, but also the problem of triggering. We are not triggering on the signal we are seeing in the oscilloscope. In addition, what happens if we have differential signals? It's very common to work with differential signals. Usually when we have differential signal, we have two options. One is to use a differential probe and to probe there. But in many cases, we are using two channels and doing math, okay, differential math. Also, many cases, well, in all the cases in the market so far, this math calculation is doing also by software. So after triggering and after maybe before doing the embedding, so it's not possible, it was not possible so far to, for instance, trigger on a differential channel, in a differential math channel. So what we are showing today is really doing real-time math. So So we have, you can imagine we have the positive signal in channel 1, the negative signal in channel 2. So what we want to do is to digitize the signal, perform difference or addition in these channels, and then triggering on this. This has never been possible so far with an oscilloscope, but it should be great to have the possibility to do this, to perform real-time mathematics so that we can trigger on this digital signal. Also, we can de-embed in real time this digital signal. So this is possible with the solution we are showing today. So again, in this case, we should be able to do this differential math in this block here in hardware. In the ASIC of the oscilloscope, this is done in real time. So we can perform the differential signal, we can apply hardware clock data recovery in real time on the differential signal, apply de-embedding and filtering on this, and triggering on this, sorry. On this de-embedded, differential, and clock data recovered signal. Okay. So, well, so far I have been talking to the techniques of using measuring eye diagrams and how can this be speed up with real-time processing. So what happens when we have a bad situation like this, that we receive a completely closed eye? What could be wrong? So then so now it comes. It's important to make an analysis of our design. So the PCB lines, if they are well designed, if there are some mismatches. So in this case, TDR, TDT analysis is really interesting. What is TDR? What is TDR? Means time domain reflectometry. Okay. So it's really measuring in time domain the reflection of signals. As we are talking on high-speed digital interfaces, it's important also to do differential TDR, real, true differential. So really measuring problems with differential lanes and detect some problems. There are some other concepts that are related to this. TDT, transmitted. We are measuring the transmission, not the reflection. And so crosstalk, the effect on other lines. We are not where the signal is not or should not stay. So who cares about TDR? Well, again, everyone who is working in high frequency, above 100 megahertz clocks, should care about this, because reflections then are really important and can be impacting our design. And how does it work, TDR? So basically we insert a signal, usually a pulse or a step, and we receive in the source smaller reflections depending on the mismatches or elements that we find in the PCB design or cable. So we can find different kind of reflections. For instance, a short or an open, in theory, should reflect everything, all the energy. So we should have in the source a pulse with the same amplitude as it was transmitting, as long as the losses are not so high. We are talking about PCBs that maybe distance are not so high, so loss should not be so high. So how does it work in our solution? So in the oscilloscope we have built in a step generator, very high frequency and very steep rise time pulse source. In the output of this step generator there is a power splitter built in, which allows to set this pulse both to the duty and to the oscilloscope, to the analysis channel analysis. So in the end, we will compare the transmitted pulse with further reflections that are coming to the input, because we have this power splitter. Depending on the mismatches, we will have different steps in the response. Okay, so we have the incident wave, or the incident pulse, that is transmitted to the DUT and to the channel of the oscilloscope. And then, some time later, we have a reflected wave, which can be added or subtracted. And depending on this step and also the polarity, we can guess the value of the mismatch, the impedance. So for instance, when we have a short, as I told you, as long as we don't have loss, we have the full wave reflected, but with inverse polarity. So in the end, we have here the original step, that is the incident wave, and then it comes back completely reflected, but polarity with the polarity inverse. So in the end, we have again 0 volts. In case of open, we have the same wave reflected, but with the same polarity. So we get in the end double the voltage of the original signal. And this time can calculating the time difference between these steps, we can calculate not only the time between these mismatches, but also the distance. If we know some parameters of our PCB, like the permittivity of the material, the electric permittivity, so we can calculate the distance. So if we have a match, of course there will not be any reflection. This is the completely matched load. And in case of any mismatch, which is different from the impedance of the source, which is 50 ohm, or in case of differential is 100 ohm usually, we can guess more depending on we will get different steps, and depending on this value, we will guess the value of the impedance. So for instance, we have this is the example of a PCB trace with different impedances. So when we send the wave into the PCB, we'll get something like this. So then with the incident wave, so we have the initial step, and then we get reflected different reflected voltage, reflected waves with different steps values. Okay. Well, here it's also important when we talk about TDR measurements and TDT, it's important to know the resolution, the minimum distance or time we can differentiate between two reflections. And this is given by the bandwidth of the system, the effective bandwidth. So this effective bandwidth of the system is measured in rise time. It's given by this RMS value, which is the rise time of the pulse. In our case, our solution have 22 picoseconds rise time, something less maybe, and also the rise time of the scope. This is the main limiting factor. So, of course, if we have a bigger bandwidth scope, this rise time will be less, so we'll have better resolution. So as long as the bandwidth of the oscilloscope is bigger, the resolution will be better. So, for instance, in case of the solution we are presenting today, 16 gigahertz oscilloscope, you will see later, including also the rise time of the pulse source, we have a resolution of 3.4 millimeters. This is the minimum distance we can differentiate mismatches or locate. We can locate the location of our mismatch with this precision of 3.4 millimeters. Okay, so what we are presenting today, and I will make a demo, is this oscilloscope here. It's the RTP. It's a brand new instrument we launched 2 months ago. It can go up to 16 gigahertz, but there are also versions with reduced bandwidth, down to 4 gigahertz. And it integrates all these new techniques I have been talking to you. Real-time de-embedding, TDR, real-time CDR, up to 16 gigabit clock. We can recover clocks on buses up to 16 gigabits per second in real time with very, very high speed acquisition. This is an example. We are de-embedding 2 channels because we want to get a differential signal. We do the differential math in real time. We trigger on this differential signal. We recover clock over this differential signal, which has already been de-embedded. And we do it in real time. We do a lot of we can run histograms, a lot of measurements, very, very, very fast, with a very fast acquisition rate. In this case, we are more or less acquiring around 400,000 waveforms per second, or UEs per second. Usually, if you go to another solution in the market, it will be running at from 1 to 10 waveforms per second. I'm not joking, it's really true, because all the other solutions do it by software, so it's really just a basic hint of what is really going there. But you cannot do real-time differential, real-time de-embedding, real-time clock data recovery. It's not possible with other solutions in the market. This is the hardware architecture. Input channel, then we have a block for real-time de-embedding, then a block for real-time math, and then we do trigger, because trigger is digital also. It's not an analog path which goes in parallel to the digital acquisition. So we trigger on the signal that has already been digitized after the ADC. So the sensitivity of the trigger is the same as the sensitivity of the acquisition, which is not the case in all the other scopes in the market. Okay, so we have the original signal, the distorted waveform, we de-embed, we can do real-time math as well, and we can trigger on this the embedded signal differential signal. Okay, I'm going to switch to the oscilloscope to show you just some of the nice features I showed you in the presentation. ¿Podrías, por favor, cambiarme la presentación al osciloscopio? Okay, so I am going to measure is a USB 3 bus. Can you hear me? It's okay? That's better like this. So a USB 3 bus, 5 gigabits per second. So it's a differential signal. So here I'm just placing my USB stick, and I'm going to measure the transmission of the USB stick into different two channels, so that I can do the differential math. I'm sorry that I cannot show you the front end of the oscilloscope and how I'm doing the measurement, but due to the disposition of the table, it was not possible. So I'm connecting these cables. This is a matched pair cable that we provide for the TDR measurements. They are especially manufactured to be really electrically the same length, to have electrically the same length. It's a matched pair cable. But anyway, they have the frequency response in magnitude and phase, and we will de-embed as well. Okay. So as you can see, this is the signal. Channel 1 is the polarity, the positive polarity, and channel 3 negative polarity. Okay. So of course they are inverted, so that's why when we have here, we are triggering here on a positive edge, here we have the negative edge in the negative channel. Of course they are inverted. So first of all, we are going to perform the different, well, I will show you the performance of the oscilloscope. Now it's working at nearly 400,000 waveforms per second. I'm clicking over this icon here. I can get a schematic of how the signal flow is going through the hardware. And in this tab here we have differential signals, the differential block. So we can calculate in real time here differential and common mode signals of every combination of our oscilloscope. In this case I'm using channel 3 for the negative polarity. Okay, channel 1 positive, channel 3 negative. So I will enable. Of course, here I have double the amplitude in the differential. So now, here I have the differential signal in real time, and here, and also the smaller signal is the common mode signal. Waveforms per second, still the speed didn't change. So I'm going to apply de-embedding. So this block here takes me to the de-embedding block. I will preset. So what we have here is the basic configuration, just the DUT and the input. So in this representation now, what we have would be like a direct connection. But we have different elements in between, so I can add to my measurement channel. I can add different elements, fixtures. I can add this cable is this model here is the match per cable, so I will use it because it's already characterized. But I could use also a generic cable, and to enter there, for instance, the S parameters. Okay, I will remove. Or this option here, proven cable, is when I want to measure the S parameters using the pulse generator included in the oscilloscope. So I can also calculate S parameters. Okay, I should go back, but I can calculate these parameters using the pulse generator as a TDR response, and then converting this to S parameters. So what I will use instead is just the model I have, just to make it quicker. And also I have this adapter here, from precision BNC to SMA. This precision BNC is the connector that is the input connector of the oscilloscope channel, of the oscilloscope channel. So as you can see, here we have this tab here is real-time de-embedding. Okay. So if I don't apply this real-time de-embedding, I can enable de-embedding, but by software. So the advantage doing by software is that it's a little more accurate, but it's much more slow, and I cannot trigger on this corrected signal. Okay. Here, if I enable, okay, real-time de-embedding. Okay, need to remove this, and I have this everything bypassed. I have to enable this. And now have the frequency response of all the elements together. Magnitude, delay, phase, and if I enable this, I get the corrected response. So we have the response of the elements, and then the calculated de-embedded response, and this is when we multiply both responses, this is the effect we have. I remove the fixture, the embedding of the fixture, because I don't have the model of this fixture. So that's why I remove it. So now the measurement plane is not here, but here, okay, in the SMA connectors, because this fixture has not been de-embedded. So I'm measuring really here in the connectors, SMA connectors. So as you can see, we are doing differential signal, we are applying de-embedding, and speed is really highly maintained. Just to show you the benefits of doing this, for instance, if we measure amplitude of the differentials on the differential signal, amplitude, maybe we can measure also rise time. No, rise time is not maybe so, in this case, so important. So it's not changing so much. But if you look at the measurement here, now we have like 940 millivolts with the de-embedded signal. I will turn it off, the de-embed, and you will see how this measurement value is changing. So now I disable the embedding. And now, maybe it's better to get the statistics. So the mean is more or less 800 millivolts, and when we apply the embedding, now it's 840 millivolts, so it's changed 40 millivolts bigger. So now we are really growing the eye. So what else? Now we would like to recover the clock from this differential signal. As I told you, we can do this this clock data recovery in real time. So we can go to Trigger menu, Source is differential, okay. Edge, we'll use this serial pattern trigger. And here we can define the bit rate of our bus, which is 5 GHz per second. Okay. So, I think there's a problem. I don't know why this is the problem with sometimes with demos in real time. I'm going to push it and get back again to get the data recovery, because it was not really well recovered. Okay, the embedding, I'm going to switch it off. Now, channel 3. We'll do differential. 100 millivolts per division. Now we have our clock, our signal. Now we are going to trigger on this differential signal. And finally, calculate the clock from this transmission. Okay, now. So now we are using the clock data recovery to build the eye, as you can see. Here we can show performance, still really, really high, 250,000 waveforms per second. And here we can, for instance, define a mask. For instance, we can define like a diamond. Mask. And you can see that, for instance, if I touch here over the PCB, it's really fast. It's real time. It's not like another oscilloscope that maybe is really slow, and if you touch, you don't see anything. I'm going to simulate, for instance. You could simulate the speed of other scopes. Well, first of all, I wanted to show with this trigger, I can not only define the CDR, but I can also trigger on many predefined standards. And also, for instance, trigger on specific patterns. For instance, if we use 8-bit, 10-bit coding, or 128-bit, 132-bit, also PRBS error in real time can be detected and triggered on this. It's really fast because it's done in hardware. But if we use just, for instance, here 0A, now I'm recovering the signal and triggering on real time on this combination of bits. Still, I'm doing mask test, as you can see, and with very, very high acquisition rate. Also, I can run histograms. For instance, if we want to measure here jitter or something like this, I could run measurements here with histograms really, really fast. Okay, I can choose here measurements on histogram, and for instance, using this value, which is here. So this is more or less the jitter. I should, of course, adjust this histogram better, but well, usually I should really stretch the histogram, something like this, more or less. As I told you, color grading is also very, very nice to see where the signal goes through most frequently. So you can see we are calculating real time differential signal in real time, triggering on this. We made kinds of calculation with really, really fast acquisition. So I think now it's time. So we'll stop here. If you have any more questions, I can show you more things later, or we can talk about these new features. Okay, thank you very much for coming.
Thank you, David, for your presentation.
Vamos a estar un ratillo más, sí, para...
Un ratillo más, ¿no?
Sí, perfecto. Voy a desmontar esto.
presentation here.
Yes, inside the...
Perhaps this.
Because in Italian. Right. Publications.